Okay, in Unit 7, you have a choice of what to do. We're going to look at two possibilities, one related to logic and one related to emergence. The Stanford AI class goes down a path of logic and looks at a number of logic and first order predicate calculus activities. Um, this is an interesting path, particularly, but it helps if you've had some logic before or some basis in math. Sometimes understand that. Um, Also, some of this is not as relevant as it used to be, and so I've added another path here on emergence and looking at that. Now, your goal is to complete 10 points worth of activities. There are activities in both. Each activity is worth 5 points, so you have to do two of them. Two activities will give you your 10 points worth. And you can choose them from either path as you go through. There's no discussions or postings this year. One of the reasons is that you should be working also on the quiz. The quiz is available here, the study guide's up, and the quiz will appear here shortly. And you should be getting ready and taking the quiz this week. So we have little shorter assignments. So let's just go over this material really quick and kind of give you a basis of it. So down the logic path that Stanford goes, it introduces you to propositional logic. Uh, so it walks you through a brief introduction to propositional logic.
But unlike in probability, our degree of belief in propositional logic is not a number. Rather, our belief is that each of these is either true or false or unknown. Now, we can make logical sentences using these symbols and also using the logical constants.
Introduces you to truth tables, looks at statements that can be either true and false and puts them together with ands and ors and implies. Um, Builds on that. We build up more complicated terminology in something called propositional logic and first order logic as we go, and builds up this syntax of or kind of functions on these operators and ands and ors and implies first order logic stuff like for alls and there exists. It introduces a world where we will look at later
Now let's go back to the two-location vacuum.
is this vacuum world where we have two locations, two rooms that can be either dirty or clean, and in a vacuum that can go between them and clean them up, and we look at the different states. We'll actually visit this problem later on again. Um, so so that's the introduction. What you can do here is watch the videos. There are some questions as he goes through, and you need to provide the answers to them. And you also need to write a sentence or two explaining your answers because the answers are given in the videos. So I want to make sure you're paying attention a little bit to those. So those are your two options. The first one just looks at the first 10 videos. The next one looks at the next set. And again, these are relatively short videos. So if you're interested in that, you can. Now, there's also links to this SICK implementation. We used to have assignments that used to have students use this download on machines, but it was a little challenging, so I've removed them. But I left the link in here because if you're really interested in this logical representation, you may want to look at this. It would be a good thing to do a final project on and work with. There are different platforms. There's an open source and other ones. This company has a database of 500,000 different terms and constructs, builds up what's called an ontology, a whole bunch of logical statements that it can reason on. There's an open source and a research version and an enterprise version that's available. And again, they have more than 1 million. Some of these have more than 7 million statements or assertions about them. They'll know things like that Abraham Lincoln was a president and of the United States. And the United States is a country, and president is the leader of that country, and Abraham Lincoln is a person. Um, so using that, we can ask questions like the author of the Gettysburg Address is on which currency, and so where Google stumbles at that, doesn't know what to do with that sort of question. Um, this, if it were phrased correctly in the right logical interpretation, should be able to reason out that that Abraham Lincoln was an author of the Gettysburg Address. That's one of the facts it will know. And Abraham Lincoln is a president, and Abraham Lincoln's on a $5 bill, and the $5 bill is currency in the United States, so it should be able to logically figure this out and go through that. So I've kind of removed that also because we are seeing some limitations to this formal logic representation of the world, and we're moving more to probabilistic representations of the world with this. So while this is still important in some areas of AI, we're seeing more research in other areas of AI. Which brings us to our next path you can choose from, and this is the emergence path. So emergence is an idea that you can have, sometimes simple rules can lead to complex behaviors. There's a couple videos here, a nice little video in Science Now, and a Radiolab podcast on MP3 that you can download on emergence. That's really good, and an article in Wikipedia about this. Let's look at these simulations of this. I'm going to run this simulation. So this is some birds flying in 3 dimensions, and they have some lines that they can collect on and work with, and it shows this sort of simulation. Let's look at one other simulation here. Let me do this first one. So again, these are birds. They're actually following my cursor around, but notice how they fly around and their rules for flying around, and they can get rather complicated, but there is some order to the whole thing. And that comes with these rules that we've seen. And so there are some researchers a number of years ago who developed these rules and really found out how we can define some real simple rules that define flocking behavior in birds and fish and animals like that. So there are 3 simple rules. One is separation. If let's just say birds right now. If a bird is close, very close to another bird, it'll fly away from that bird. Another one is alignment. If a bird isn't has just some neighbors around it, it will tend to fly in the same direction as the neighbors. Average the neighbors out and fly in that direction. And cohesion, if the bird is by itself and there's no one around, it will look around to a set of neighbors that it can find and fly to the midpoint of those neighbors. So we can define these radiuses of how close we avoid birds, how much we do alignment, and how we do cohesion, how many birds we look, and set those rules and those radiuses. It's not very hard to define those rules and then program them in, and we can get this complex flocking behavior that mimics real-world flocking behavior amazingly well. So that's one example of an emergent behavior based on simple rules. Here's another example of emergent behavior, and this is Conway's life simulation. So I'm going to run this version of it because it gives a nice overview. So Conway's life simulation, we have a grid with some life forms on it, like maybe mold or bacteria or people. And so each grid spot either is alive or is empty. And we can put down some initial values here. And then we can have this change these values over time. And there's rules for changing these values. Let's look at those rules. So in the grid, any cell that has fewer than 2 neighbors. So we look at a grid and then the 8 neighbors around it. If it has fewer than 2 neighbors, or 2 or fewer than 2 neighbors, it dies of loneliness or underpopulation. Any cell with 3 neighbors, more than 3 neighbors, dies of overpopulation. Any cell with 2 or 3 neighbors lives for the next generation. So they like to have 2 or 3 of the 8 neighbors alive, and it stays alive. So those are the rules for live cells. Any empty cell, if it has 3 neighbors, it becomes a live cell by reproduction. And we can look at simulations of that. Let's look at this simulation. So I can draw out a pattern here, or a set of values, and then I can run this. and it'll generate some updates of this, and we can get some very complicated behaviors from these relatively simple rules. So here the blue cells are alive, any non-blue cells are empty. Green just shows where we've seen some life. We can actually set up some random grids and try this again. And you can actually change some of this behavior and some of these. You can change some of the rules and runs this. Conway wife is an example of something called cellular automata, which again has simple rules to generate these complex behaviors that run. Another way I want to look at is chaos. So the idea of chaos is that small changes in some equations or some systems can generate very complicated results as we go. So here's just a simple pendulum with a joint in it spinning around, and we get some very complicated results as it moves around. Um, the idea is that things like the weather system are very dependent on what we call initial conditions, that small changes can affect the behavior over time. That's why in some ways it's so hard to predict the weather, because slight changes in the current system make very drastic changes in models and also in the actual weather later on. The stories often said that a butterfly flapping its wings in California can make the difference between a rainstorm and a snowstorm in Europe 4 days later. We'll look at one example of this logistics function, which is this function y equals x times 1 minus x, and we put a term like 2 or 3 or 3.5 in here. But this simple equation gives us very complicated results over time, and we can explore what it does in some ways. And so there's an activity down below where you can look at that. The last thing we're going to look at is fractals. Again, fractals have relatively simple equations set up that give complicated results. Here's the Mandelbrot set, and the idea is that this looks at x and y coordinates that go from like 0 to +2 and -2, and same up and down. And we work with a simple set of simple equation where we take a point, run it through this equation, and get a new point and run that through the equation. Easiest way to write these equations is with imaginary numbers, but you can just translate it into normal number systems, and that's what we'll do in this class. And then as you iterate the same number through the same equation, the same function again and again, sometimes the results always stay small, like under 1. And so every black dot in this graph or grid shows a point that stays small. But the numbers, the colors show that some of our points get larger, and the color is chosen depending on how quickly some of the points get larger. So you can see still these black points being inside the equation, and so these are points where as we iterate them over and over again they'll stay small, but there are other points nearby where we iterate them, they'll get larger and larger. So you get some very complicated behaviors in this graph from relatively simple mathematics. Okay, so that's kind of your overview of emergence. So you have 3 activities to choose from, 4 activities to choose from. One is the game of life, Conway's life. You can run different simulations, and there's some questions you need to answer on Conway's life. Another one is on the logistics theory and chaos. We look at this equation here and try different values for this R, and we see different results as a result. So you have to do some computations there. Another one is fractals. We actually have you try out the Mandelbrot equation. There's an equation for how you recalculate x and how you recalculate y at each time. So you get a new point based on the previous point, and there's a spreadsheet that'll help you calculate those values and see if you can see and then determine which of these values are in or out of the Mandelbrot set. The last one you can look at is flocking behaviors. You can actually run some of these flocking examples and there's some questions about those you can do. So those are your 4 activities here, and remember you also have the 3 activities under logic that you can choose. And again, remember you just have to get 10 points. Each activity is worth 5 points. And again, it is simplified this week so that you can spend time on the quiz 1. So good luck.